Hi again. One quick note on the last on the graphing notes before we get to position, velocity, acceleration graphs is it's always a good idea to try to give an example of what a particular graph might represent. So for this first set that we did, where we have a constant positive, where the displacement is positive and increasing the whole time at a constant rate, we could the velocity is constant. There is no acceleration. We could say that this is a person who's simply walking forward at a constant rate. For this second one, where we have the displacement is becoming more positive the whole time. However, we have a changing slope. At first, our slope is increasing. We have a positive increasing slope. Then we have a positive but decreasing slope. Velocity goes up and then back down, starts and ends at zero. And we have constant positive acceleration to begin and constant negative acceleration at the end. We could say that this is perhaps a car accelerating from rest then stopping, so it has to slow down, at a stop sign. Car accelerates from rest, gets up to speed, but then it has to decrease its velocity to slow down for that stop sign. Okay, so we're going to do that in these next examples as well. Okay, so position, velocity, and acceleration graphs. We're going to do pretty much the same thing with these. So let's look. This first one, we're going to analyze these pretty much the exact same way. This first one, let's think about the questions that you know to ask for graphs. We have a position or displacement that is positive the entire time. Okay, we have a slope that is positive the entire time. In other words, the position or displacement is increasing the entire time, so slope is positive, and the slope is becoming more positive as we go. So, remembering our facts that we know, the slope of a position versus time graph is the velocity. Since the slope is positive and increasing, that means our velocity should be positive and increasing. Like that. We are going to assume constant acceleration for this. Remember, we assume constant acceleration. The acceleration can change instantaneously, but it will not steadily increase or decrease in these cases. Okay. Okay. So we have a velocity from that first graph. We know that we have a velocity that is constant, or that is increasing and positive. We know that the slope of a velocity versus time graph should be the acceleration. We notice that our slope here is constant. It is the steepness of the line does not change. We also notice that it's positive. So if our slope of velocity versus time is constant and positive, the acceleration must also be constant and positive. And if you look, that very last one that I just reviewed on the last page, it's kind of just like the first half of that is just kind of like this. So we have a constant and positive acceleration, which causes a increasing positive velocity, which causes our position to increase in this sort of shape. It should be parabolic. I couldn't quite draw it on the computer. What sort of motion is this? Imagine that this is an object accelerating from rest. At constant velocity, or excuse me, at constant acceleration. Okay, it's as simple as that. Now, what if we're given the velocity graph first? My preference, you could start by doing this one first. You could start by doing this. My preference is always to go kind of towards the right on this. You want to go towards acceleration first, then you can go back. That's the easier one to do, is going to the right first. So we've got a velocity versus time graph. How do we describe it? Well, the velocity starts off very high and then decreases. In other words, that means the slope is negative. Okay? We know the velocity is positive the entire time, but the slope is negative. And what that really means is, since this is a velocity versus time graph, if the slope is negative, that indicates to us that the acceleration is negative. Since the slope is constant, that means the acceleration is also constant. So we have a constant negative acceleration. That would look something like this. Okay? Now, it does tell us to assume that x naught is 0, so I'm going to do that. I'm going to put a little dot right here for x naught. And now we can use some other facts about the v versus t graph to kind of guess as to what this, or not guess, but to figure out what this should look like. Remember, the area under a velocity versus time graph is is how the displacement changes. This area here would all be positive because it's above the x-axis. So I should be gaining displacement here, okay? And that means, since I start at 0, my graph should be in the upper quadrant here. Since the velocity starts off high and ends up at 0, and since I know that the position versus time, or displacement versus time graph, the slope of that graph should be the velocity, I need a slope that is very high initially and goes towards 0. That would look something like this. Okay? I have a slope that's very high in the beginning, indicating high velocity, and then over time, that slope, that steepness, decreases until it flattens out, gets to about 0 at the end. There we go. And okay, so our first graph, our position versus time graph, says it corresponds to this. And since we know that the velocity is decreasing, but or the velocity is decreasing, which means the slope is negative, but that slope is constant the whole time, I have negative constant acceleration as well. Okay, let's do some more. Let's do the third one. Oh, actually, before we get there, describe this motion. What could this be? This could be something where, this is kind of like, again, the second half of this. So object was moving quickly, then it slowed to a stop. Okay? And we say slowed down because, as you'll notice, and maybe you'll remember, if your velocity and your acceleration have different signs, that means you have an object that's slowing down. This is a positive velocity the whole time. Look where all the velocity points are. They're all above the x-axis. It's positive velocity. Negative acceleration, we have an object that's slowing down. For this first example, we have positive velocity the whole time, positive acceleration the whole time. It's all above the x-axis, which means the object is speeding up. It's gaining speed. How about this one? What's happening here? We start off with a very high slope and we go to a lower slope. This is an object that is slowing down. Okay. Beyond that, we have, let's see, asking our questions, we have a displacement that is always positive. We have the displacement decreasing, or the position decreasing, which means that the slope is negative here, which means our velocity will be negative. And we have a slope. The way the slope is changing changes from a very steep slope to a not so steep slope. So our slope is going towards 0, okay? It's actually becoming more positive if you think about it. It starts off as a very negative slope, becomes very close to 0, so it's not going towards negative infinity for the slope. It's actually going towards positive infinity, so that's interesting. Let's do the v versus t graph first, though. So we know that the slope is negative, and we know that it's changing. It starts off with a very high slope, a very negative, very steep slope, and it goes towards 0. So I think what that should mean is we start here, and we have a graph of velocity that goes like this. Okay? We know it has to go towards the x-axis because we know the slope down here is almost 0, so we know that our velocity here should be almost 0, since we have a position versus time graph, and the slope of that graph is equal to the velocity of the object. Okay? Now, we can do the same thing with the velocity versus time graph. We have, interestingly, a positive slope here, and it's a constant positive slope. Slope of velocity versus time is acceleration, so our constant positive slope means a constant positive acceleration here. And that is confusing to people as well. But think about it, you have a negative velocity, all the velocity points are below the x-axis, you have a positive acceleration. This object is slowing down. It's just slowing down in such a way that it was moving backwards the whole time, and it's coming to a stop. So this would be like if your car is in reverse, but you're slowing down to a stop. Okay? Make sure you understand the idea that velocity and acceleration do not have to be in the exact same direction. All right, let's do our last one. We have a very funky looking graph here. We have a velocity that starts at 0, it goes down, it goes towards negative infinity, then it blasts up very quickly in a very short amount of time, and then decreases back to 0. So that's interesting. Again, we're going to do the acceleration first. I have an acceleration, let's see, acceleration should be the slope of my velocity versus time graph. Just looking at, answering the questions, I have both negative and positive velocities here, so that's interesting. I know that my velocity is decreasing. We have a negative slope, then a very steep positive slope, and then another negative slope. Okay, and except for here and here, all of those look like constant slopes. Okay, except for these points right here and here, which we won't deal with too much. Okay, so velocity versus time graph. I have a negative slope to start out. Negative slope on a velocity versus time graph means negative acceleration. And it's a constant negative slope, so it should be a constant negative acceleration for that first, just about half. And draw it like that. Then I have a very, very steep upward positive slope. Okay? Since this is a velocity versus time graph, the upward slope the positive slope indicates a positive acceleration, and it's only for a very short period of time. So I'm basically just going to almost draw this straight up, like this. Probably should be even taller than that. And then I get another negative slope. Okay, so the acceleration must be negative on the other side of this. Okay, make sure you understand that. The negative slopes here lead to negative accelerations. The negative slopes on my velocity versus time graph lead to negative accelerations. The very positive slope leads to a very brief positive acceleration here. We're assuming that x naught is positive. So that means x naught's going to start up here somewhere. Look at the area under the curve. This area here would be negative because it's below the x-axis. So I should expect a loss of position. Then I have a positive area under the curve here because it's above the x-axis. Then I should expect a gain in position. So I have a negative, let's see here, I have a negative slope, my velocity is negative here. That should mean, since this is a position versus time graph, that the slope, starts out at about 0, but decreases to something pretty negative. So that would be kind of like this. Okay. Then I have a very quick upward positive velocity. My velocity changes. So right here, I have a slope that starts off negative but becomes positive very, very quickly. It rebounds, and then I have a positive slope that slowly goes back towards 0. So how would I draw a positive slope that slowly goes back towards 0? Here's a positive slope. It occurs almost right after it gets to this point. So I've got this very positive slope, but that slope is decreasing until it gets back to about 0. Okay, and if you look at this, you can tell that this graph represents the same thing that this one does. We start off with a slope of approximately 0. Since this is a position versus time graph, that means that the velocity should be approximately 0. The slope decreases, meaning the velocity decreases. Then I have an almost instantaneous kind of switching of the slope. It was very steep and positive, and negative. Now it's very steep and positive. That's this right here. I get up to a very positive slope, but that positive slope decreases again towards 0, just like I have here. So believe it or not, these three graphs all correspond to one another. And the motion that would cause this is actually a pretty common motion. This is the motion of something bouncing. And you can kind of see that in this shape right here. It almost looks like something bouncing. But if you think about how something would bounce, it falls towards the ground. It has negative velocity that gets greater and greater. When it bounces, it now is moving in the opposite direction. Now it's moving up. So we have a spike here that goes and changes the velocity to now be positive. But as soon as it's off the floor, it's going to start losing that velocity again until it reaches the peak of its bounce, which is right here, where it again is not moving, and then it would repeat, and then it would go down, spike up, go down, spike up, if it was allowed to keep bouncing. For something in free fall, we know the acceleration is constant and negative. The only time it's not in free fall is this spike right here, when it's in contact with the ground and the velocity is being changed so that it's now upwards. Okay? We'll pick up with 4 more of these to finish up this section of notes in just a little bit.